Welcome back to What is Time Part 4 with P. Edward Swan. We are still working on the same problem. How do we synchronize two clocks that are experiencing different environmental interactions? If we have two identical clocks and we take one of the clocks on a journey around the solar system, how can we make sure the two clocks are synchronized at every step of the journey? To synchronize two clocks, we must measure all the environmental factors that each clock is experiencing, and then we must adjust for any variations. In this final video of the series, we will complete our tests. We will use the variability of clock cycles to detect and measure the underlying motion of our spaceship. In the previous video, we accelerated some clocks, and by observing the changes in their cyclical outputs, we found the direction of motion of our spaceship. Now we just have to do one more test to determine the speed of our spaceship. To find the underlying speed of our spaceship, we can use our clock accelerator to take one more measurement. In Part 3, we calculated that the direction of motion of our spaceship is northeast at the angle 1/8 pi from the x-axis as shown in the figure. To begin our final test, we line up the clock accelerator at the angle 1/8 pi, and we accelerate clock A exactly as in the previous tests. Clock A will be accelerated to 10% of the speed of light back and forth along the direction of motion of the spaceship. Because the clock accelerator is exactly parallel to the direction of motion of the spaceship, any acceleration will be a 100% addition or a 100% subtraction from the speed of the spaceship. Just like before, we add the velocity vectors. But for this test, we are only interested in the additional velocity vector from clock A that is in the direction of the underlying motion of the spaceship. We will add that to the velocity vector of the spaceship to get the total velocity vector for clock A. Please recall we do not know the length, 8% of the speed of light, of the velocity vector for the spaceship at this time, and we will have to calculate that length indirectly by observing the clock cycles of clock A and clock B as we perform this final test. And here we have the extra velocity vector that we're adding from the clock accelerator, and that's the light blue, and this we know. And then we have the base velocity of the spaceship, which is this darker blue, which we do not know, but we know the direction. And that gives us a total velocity vector, this dotted yellow vector, which is unknown. And we will have to calculate that length in the future when we get more information. But we do know the direction of this total velocity vector. To get the data points we need to solve our equations, we must record the number of clock cycles produced by both clock A and clock B when clock A is in the clock accelerator at maximum speed. In the figure, we revisit the velocity curve for clock A when it is in the accelerator. We start counting the clock cycles of clock A when the accelerator reaches full speed, the green dashed line, and we stop counting the clock cycles of clock A when the accelerator begins to slow down, the red dashed line. The accelerator also sends a light pulse to clock B at the same 2 points to start the counter for clock B and to stop the counter for clock B. Since clock B is not experiencing any accelerations, the number of clock cycles recorded and counted for clock B will be statistically equivalent over any equal intervals. Therefore, any delay in starting and stopping the counter for clock B caused by the distance the light pulse must travel will not affect the outcome of the experiment by any material amount. Okay, so we have clock A in the clock accelerator, and we have clock B right next to the clock accelerator. Clock B is at a constant velocity equal to the spaceship. It's attached directly to the spaceship. And clock A also is on the spaceship, so it has the same constant velocity of the spaceship, but it will also have an additional velocity when it's in the clock accelerator at maximum speed, which is between the green dotted line and the red dotted line. When clock A is accelerated and hits this green dotted line, this green laser, the green laser will start clock A. At the same time, that will break the laser light hitting clock B, and that will start clock B. So the break in the laser starts clock B. When clock A hits the red dotted line, the red laser, it will stop the counter for clock A. At the same time, it will break the red laser, and that break in the red laser will stop the counter for clock B. In that way, the mechanical motion of clock A while it's in the accelerator will start and stop both clocks in the same interval. And that's how we'll perform this experiment. Now we have to calculate the number of clock cycles that will be recorded by clock A and clock B when clock A is in the accelerator. To do this, we have to imagine a third clock. There is a clock R, for rest clock, that is somewhere in space far away. Clock R is the ideal clock of identical construction to clock A and clock B that is not experiencing any motion, gravity fields, heat, or any other factors that would cause it to run slow. Now we can calculate the time dilation of clock A and clock B against this ideal reference clock R. Compared to clock R, how many cycles will be counted for clock A and clock B when clock A is in the accelerator at maximum speed? For this example, all of the calculations are based on the number of cycles of an atomic clock per second. First, we will calculate the number of clock cycles produced by the ideal reference clock, clock R. Because clock A is moving relative to the spaceship at 10% of the speed of light, and we need to cover 10 meters on the spaceship, then it would take clock A 3.34 times 10 to the negative 7 seconds, about 3/10 millionths of a second, to travel that distance. An atomic clock at rest would tick approximately 3066.33 times in that interval. To calculate the number of clock cycles produced by clock A, we use the time dilation equation as shown, and we plug in 18% of the speed of light for the velocity, and we get the Lorentz factor of gamma equals approximately 1.016604. Therefore, the number of clock cycles produced by clock A is equal to the clock cycles recorded by clock R divided by the Lorentz factor. Clock A will record about 3015.92 cycles when moving at 18% of the speed of light, compared to clock R that records approximately 3066 clock cycles. The same calculations are shown below. Next, we calculate the number of clock cycles produced by clock B during the test. We will use the same time dilation equation, but this time we use the speed of the spaceship for clock B. Therefore, we plug in 8% of the speed of light for the velocity, and we get the Lorentz factor of gamma equals approximately 1.0032154. Therefore, the number of clock cycles produced by clock B is equal to the clock cycles recorded by clock R divided by the Lorentz factor. Clock B will record 3056.17 clock cycles when moving at 8% of the speed of light, compared to clock R that records 3066 clock cycles. Again, the same calculations are shown below. We have calculated the number of clock cycles that will be produced by clock A and clock B during the test. Now we can compile a list of the known and unknown values we have at this point. Known and unknown values. Speed of the spaceship is x. This value must be calculated. Speed of clock B equals the speed of the spaceship. Again, x, which must be calculated. Speed of clock A is the speed of the spaceship plus 10% of the speed of light. This value must be calculated because we don't know the speed of the spaceship. Number of cycles produced by clock A equals 3015.92 cycles. That value we found out during the test. Number of clock cycles produced by clock B equals 3056.17 cycles. We also found out this value. It was measured during the test. Number of clock cycles produced by clock R equals y. This is a value we must calculate. So we have two unknown values that must be calculated. The speed of the spaceship, x, and the number of clock cycles produced by clock R during the test. We have two equations and two unknowns, and therefore we can solve for these variables. Our known values are the additional speed of clock A is 10% of the speed of light. The number of cycles produced by clock A during the test is 3015.92. The number of cycles produced by clock B during the test is 3056.17, and we also know the speed of light, which is a constant, 299, 792, 458 meters per second. Now we use the time dilation equation stated in terms of delta t, or the rest clock, clock R. And here we have that equation, and we'll plug in the different values to get two equations, equation number 1 and equation number 2, one for each clock, clock A and clock B. Using the information from the list above, we start with clock A, where delta t prime, the number of clock cycles recorded by clock A during the test, is equal to 3015.92 cycles, and velocity v is equal to x plus 10% of the speed of light, which x is the speed of the spaceship. So there we have the number of cycles produced by clock R will be equal to the number of cycles produced by clock A, delta t prime, times the Lorentz factor. So here we have delta t equals 3015.92 times the Lorentz factor. We plug in for the velocity, we plug in the speed of the spaceship plus 10% of the speed of light, and for c is the speed of light, which is a constant, and we plug that in here, and now we have equation number 1. Then we plug in the numbers for clock B, where delta t prime, the number of clock cycles recorded by clock B during the test, is equal to 3056.17 cycles, and velocity v is equal to x meters per second, which is the speed of the spaceship. So here again we have the same equation with clock R is producing some number of clock cycles given by the number of cycles produced by clock B times the Lorentz factor. So we have delta t equals 3056.17 times the Lorentz factor, where here we use the speed of the spaceship for clock B for the velocity, and we plug in the speed of light for c. And then we have our two equations. We have two equations with two unknowns, and both of the equations are already solved for delta t. Therefore, we can use substitution to create one equation with one unknown. We start with equation number 1, which is the relationship between delta t, the number of clock cycles for clock R, and clock A clock cycles produced during the test times the Lorentz factor. Then we substitute the value of delta t from equation number 2 into delta t in equation number 1, and we have the following equation, which is the number of cycles produced by clock B and the number of cycles produced by clock A. This is the relationship between those two things using the Lorentz factors for both of those clocks given their different velocities during the test. Now we cross multiply to simplify the equation before we plug this into an equation solver. And then we get this next equation, which we'll plug into the solver. And the easiest way to solve this is to plug it into Wolfram Alpha. Thank you, Wolfram Alpha. The figure shows a snippet of the web page with the input and the solutions. The solution is x equals 23,983,396.64, where x equals approximately 8% of the speed of light, which is correct. Now we can solve for delta t, the number of clock cycles produced by clock R, the ideal clock at rest that has no velocity. To do this, we go back to equation number 2 and we plug in the value that we just calculated for x. So here we have equation number 2. We plug in the calculated value of x, which is 8% of the speed of light. We plug that in for the velocity v. We plug in the speed of light, which is a constant. And now we just do the algebra and we get 3066 clock cycles for clock R. We have solved for both of the unknowns and we are done. For those of you die-hard mathematicians, you can see the step-by-step work-through of the problem shown here. For the rest of us, we'll be moving on. So now we have shown that we can calculate the velocity of a spaceship by using multiple clocks, subjecting those clocks to different environmental variables, and observing only the output of the clocks. That is, we can count the clock cycles. In practice, we would need to keep careful control of all the environmental variables of the system. We would need to account for any changes in the clock cycles due to heat, distance contraction, relativistic mass, the gravitational fields of the spaceship, and possibly other variables that are still unknown to science. And of course, at this time we do not have a clock accelerator that can accelerate objects to 10% of the speed of light. Let us consider some similar methods that may be more pragmatic. As an alternative, we could shoot atomic clocks out of a railgun at about 3,000 meters per second. However, at this speed, atomic clocks are not sensitive enough to detect the change in velocity. By my estimation, we would need a clock that will produce at least 1,000 times more cycles per second than an atomic clock. Or we would have to shoot about 1,000 atomic clocks out of a railgun and take the average of the results to get a semi-workable measurement. Also, atomic clocks may just break if they are shot out of a railgun. In any case, we would end up with a pile of broken clocks at one end of the spaceship. A railgun might work, but it is not an ideal solution. A more interesting possibility is to use spinning objects instead of the theoretical accelerator proposed in our thought experiment. If we made a spinning wheel with atomic clocks embedded at the periphery, and the wheel is spinning at 100,000 revolutions per minute with a radius of 10 meters, then the clocks would have an additional speed of about 105,000 meters per second. To perform our tests, we would need to isolate the motion to just a single direction, so we would need to take measurements only when a clock is moving in one of the primary directions, north, south, east, west, up, or down. Therefore, we could limit the measurements to 12 degrees of the rotation. Then the motion of the atomic clock is primarily in one direction. Based on these assumptions, it would take about 29 seconds of runtime for an atomic clock to detect the required variance. The longer the machine rotates, the more information would be collected and the more precise the information would be, provided we could build a rotating system that would not fly apart at 100,000 revolutions per minute. If we added more clocks to the spinning wheels, then we would collect more information per rotation. Also, a three-wheel system, at right angles, has two clocks moving in each major direction at all times. Therefore, we could collect more information and detect the required variances in less time. As clocks become smaller and more precise, we can fit more clocks on each wheel. With 3 wheels and 1,000 clocks per wheel, we would be able to take about 100 complete measurements per second. The ultimate goal is to design a clock system that self-adjusts to a universal standard of time. Right now, the standard for time is the NIST definition, which is 9,192,631,770 cycles of a standardized cesium atom per 1 second. But as we know, any physical clock is not perfect and will produce variations when it is subjected to environmental conditions. Instead, a universal standard of time must be based on the number of clock cycles of an ideal clock. An ideal clock is an imaginary, high-precision clock at zero velocity and some standard heat and zero gravity and possibly more variables. To build a self-synchronizing clock, we must design a clock system that detects all of these environmental variables and constantly adjusts itself to the ideal universal standard. The clock system must measure any accelerations and gravitational fields and heat gradients that it is experiencing, and then keep track of them all to calculate the never-ending series of adjustments that would be needed to reconcile itself to the universal standard of time. Yes, we have a lot of work to do before we can realize this dream. In our thought experiment, using just 2 clocks, we were able to detect one environmental variable, namely the motion of the spaceship. The more clocks we have, the more environmental factors we can detect and calculate. How can we use clocks to detect environmental interactions? The answer to this question can be found in my book, Darwin's Machines. There you will discover a powerful new tool called a clock array, imagined by me, P. Edward Swan, that would, in theory, allow any 2 clocks to be synchronized given enough high-precision clocks and sufficient information processing resources. The science of time is just barely getting started. The future will be filled with clock systems that will have trillions of simple oscillators networked together to create machines that will begin to decode the very nature of matter and energy at the smallest scales. These machines will be like a mathematical microscope that will calculate all of the hidden processes and particles at the very heart of existence. This series builds on the ideas in Darwin's Machines 2024. Thanks for watching, and if you want to go deeper, check the links below for the next video.